Hey, Dr. Kennedy,
Yeah.
I have a question. It's not on the review or anything, but going over the homework from the 16th, number 3 kind of threw me off a little. I wasn't entirely sure how to go about doing that one.
Oh, okay. Well, all right. Well, I'll tell you what, if there's time at the end of the hour today, I will work. Okay, the 16th you said?
Yes, ma'am.
Okay, so that's the intermediate value problem?
Yes, ma'am.
Okay. We'll go over one of those at the end of the hour. Okay.
Sounds good. Thank you.
Okay, it's 8 o'clock. Okay, let's see. Yeah, I figured out how to save my files, the notes files, as PDF files, and also send them to myself. So everything, all the notes are now posted, and the update improved the appearance of them quite a bit, actually. Okay, practice exam is posted, homework solutions are posted, and all the recordings through yesterday are posted. So everything is up to date and you can use it to study with. Exam Friday, I must be able to see you on camera. Okay. If I can't, then I won't take your exam and we'll arrange for you to take it on campus later. What else? Same rules. You can use your notes, but no electronic devices, not to help you work the exam. I must be, yeah, you have to use them so I can see you and so you can get and sit in your exam. We will review tomorrow. Any questions? Okay. Well, okay, we're going to review tomorrow. And if you remind me, that was Daniel talking?
Yes, ma'am.
Okay. If you remind me, I'll go over that problem 3
Okay.
at the end of the hour. Okay. Okay. All right, so that's the other class. There. Okay. Can everybody see my screen?
Yes, ma'am.
Okay, good. We have been talking about integration for over a week now. Today, we're going to get your very first technique of integration, okay? And it is called substitution or U substitution. Okay. Let somebody in. Let me do that. Okay, and this is going to utilize, well, the inverse of the chain rule. The chain rule says that the derivative of a composition of functions, so f of g of x is inside f, so to speak, that derivative is f prime of g of x times g prime of x. Well, if that's the case, then the antiderivative of this should be that, okay? And that's what the next line says. The trick is recognizing when you've got this form inside your integral. And okay, so the substitution rule is kind of about that. It says that if u equal to g of x is a differentiable function whose range is an interval I, and f is continuous on I. So these hypotheses are just to make sure that f of g of x really makes sense, okay? And you've got the thing defined on an interval. But if that's true, then the antiderivative of f prime of g of x times g prime of x is the antiderivative of f prime of u du. Okay, so what are we doing there? We're replacing g with u. What we're doing is taking the original integral that was given in terms of x, okay, that's your variable for the integral, and switching that variable over to u. But you do it carefully. Okay. Yeah, u is g of x. And that means that du dx is g prime of x. Okay, that derivative of u is equal to derivative of g. You can think of du and dx as being something called a differential. Okay. And if you're going to kind of pull it apart, g prime of x dx is equal to du. Yeah, differentials. So you're not going to do a lot of arithmetic with these, but we are allowed to do this. So that means that g prime of x dx is replaced by du. And let me show you an application. I've got the integral of x cubed cosine of x to the fourth plus 16 dx. Okay. Well, what you want to notice is that inside the cosine function, you have x to the fourth plus 16. And what's the derivative of x to the fourth plus 16? Derivative is 4x cubed. Okay. Fours can come in and out of. The important thing is that I almost have that derivative sitting there for me. Having that derivative there is really important. So what you're looking for when u substitution is going to be useful to you, you're looking for a function inside your integral somewhere, and then the derivative of that function sitting outside. Well, outside the other function, not outside the integral. Okay, so what do I
Will it
mean?
always be like that?
Always. What's always?
Like, well, all these functions like this, would it have the derivative on the outside like that in the front?
Yeah. This is a pattern you want to learn to see. Okay, learn to recognize when it occurs. But let me go through the details here. Okay. So what I want to do is change my variable from x, like it is here, to u, in the hopes of making the problem easier. So I want to let u equal to x to the fourth plus 16. So that means that du dx, my derivative of u with respect to x, is 4x cubed. So du is 4x cubed dx. And okay, the 4, well, I don't see that 4 in my original integral. but that's easy to compensate for. Just multiply through by 1/4. So I have 1/4 du is equal to x cubed dx. And now I'm going to use this to change my variable from x over to u. So here's my original problem. One-fourth du replaces x cubed dx. Okay. And what's the rest of it? Well, it's the cosine of u. U is x to the 4th plus 16. Okay. And so I have changed my variable from x to u. And this integral is much easier to do. 1/4 cosine of u. It's easy to get the antiderivative for that. I can pull the 1/4 out. And antiderivative of cosine is sine. And you add your arbitrary constant and put back in the x's. So 1/4 sine of x to the 4th plus 16 plus c is my antiderivative. Okay, so it worked very nicely in this problem. Questions?
Why did you multiply it by 1/4?
Pardon?
Why did you multiply it by 1/4?
Because 4x cubed is not inside my integral. Okay, it's just x cubed.
Okay, I see.
Yeah, so x cubed, and that's, yeah, have to have it.
So you basically just divided both sides by 4.
Yes.
Gotcha.
Yeah. Okay. Okay, so let's look at another one. Oh, how about this? We can now find an antiderivative for the tangent. That wasn't in our list before, right? Because it's not so straightforward. We know what the derivative of the tangent is. It's the secant squared. So the antiderivative of the secant squared is the tangent, but we don't know what an antiderivative of the tangent is. Well, what if I do this? Oh, no, wait. No, I can't tell you about that yet. Sorry. Okay, by next week I will be able to. I forgot about something. Let me pick another example. Yeah, okay. By next week we'll be able to do that, but I have not covered something yet that needs to be covered first. Okay, how about this one? The antiderivative of 3x plus 4 dx. Well, the problem here is that I've got that, well, the 3x plus 4 under the square root. And that makes it a little bit difficult to deal with. But it's really just a linear thing under the square root. So a u substitution will work here too. Yeah, the 3x plus 4 is a problem. I want to change it to u, okay? So I'm going to let u equal to 3x plus 4. And well, will that work or won't it? Sometimes you guess the wrong thing for you, or sometimes U substitution is not going to help you at all. First of all, it only helps sometimes, but it will help here, I think. If we let u equal to 3x plus 4, then du dx is 3. So du is 3 dx. Well, I only have dx inside my integral, not 3 dx. So divide both sides by 3. Dx is going to get replaced by 1/3 du. Okay. So that changes the problem. To, okay, 1/3 du replaces dx, and that square root now becomes the square root of u. I can pull the 1/3 out because it's a constant, and write that square root of u as u to the 1/2. And then take my antiderivative, okay? So it's going to be u to the 3/2 over 3/2. And that's equal to, okay, 1/3 times 2/3. And u is equal to 3x plus 4. So 3x plus 4 to the 3/2 plus c. And I may as well multiply. That's 2/9 3x plus 4 raised to the 3/2. Okay, questions?
No, ma'am.
Okay. Yeah, a lot of times students will ask me, well, where did the X go or whatever? Yeah, well, you changed everything carefully from X over to U. Okay, let's try another one. Let me find a good problem here. Let's see. How about we do a definite integral with one of these. How about this? Okay. The antiderivative, definite integral rather, 0 to pi of the secant squared of t over 4 dt. Okay, well, we know what the antiderivative of the secant squared is. That's tangent. Only problem is we got t over 4 in there instead of just t. But I think we can take care of that by changing our variable t to a variable u. We let u equal to t over 4. So that says du dt is equal to 1/4 dt. Oops, wait a minute. have the dt on the other side. Okay. So yeah, du dt is 1/4. That means that du is 1/4 dt, and 4 du. Well, there are two ways. Now, this is a definite integral. Got that? So that means I'm supposed to come out with a number. But, okay, there are two ways you can go here. You can either change your endpoints over to u and then evaluate the whole thing, or you can get an antiderivative first and then go back to your t's and then evaluate. I'm going to do it both ways. So so an antiderivative of the secant squared of t over 4 dt, so indefinite integral. And I want to make this substitution. So u is t over 4, and 4 du is going to be dt. So can replace everything. This is equal to, 4 du, and my function is the secant squared of u. Okay, then I can bring the 4 out of the integral. And any derivative for secant squared is tangent. Only I want that in terms of t over t, okay, not u. So that's 4 tangent of t over 4 plus c. Okay, so that's the indefinite integral. But I had a definite integral, okay, integral from 0 to pi. That means then the integral from 0 to pi of secant squared of t over 4 dt is equal to, okay, we have an antiderivative for that function. Sorry. It's 4 tangent of t over 4. And I want to evaluate that from 0 to pi. And that's going to be 4 times the tangent of pi over 4 minus 4 times the tangent of 0. Well, the tangent of 0 is 0. The tangent of pi over 4 is 1. So it's 4 minus 0 is 4. Okay, that's one way you can go with this definite integral. Let me show you another. I don't have to come back to my u's to the t's at all. So let's see, we have the integral from 0 to pi of the secant squared of t over 4 dt. We made this substitution. U is t over 4. And we got that, let's see, 4 du is equal to dt. Right, okay. Well, since I'm changing my, wait a minute, I got a u there in my integral instead of a t. There, okay. I'm changing everything over to u. So my t's in this definite integral, 0 is less than or equal to t is less than or equal to pi. And that's what the dt says. I want t to represent it, all the numbers between 0 and pi in some sense. But that's my endpoints in terms of t. What are they in terms of u? Okay, well, this would say that 0 over 4 is less than or equal to t over 4 is less than or equal to pi over 4. or 0 is less than or equal to u is less than or equal to pi over 4. So I'm changing my endpoints over 2. And that means my new integral, one in terms of u, goes from 0 to pi over 4. And let's see, 4 du replaces dt, and I've got secant squared of u. And that's equal to, okay, let me come down here, 4 times the integral from 0 to pi over 4 of the secant squared of u du, which is 4. Antiderivative of secant squared is u. And that gives me 4 tangent of pi over 4 minus 4 tangent of 0. So the same thing as before, we get 4. Okay, so you could do either of these things when it's a definite integral. Any question?
Could you scroll back down to your final answer?
Scroll back down, yes. There?
Yes, ma'am. Thank you.
Okay, let's see. I'm picking out another one. How about this? With that denominator, I better have a numerator that matches up. So let's see, how about okay. Yeah. Oh, let me mention something. If I didn't have that 2 plus 9x squared in the numerator of that thing, well, good luck in getting an antiderivative. Yeah, U substitution's gonna work here, but precisely because I have the derivative of this function under that square root sitting there in the integral for me. Okay, that's what you want to look for here. A function embedded in another function, some function, but then you've got its derivative sitting outside for you. So I'm going to let u equal to 1 plus 2x plus 3x cubed. Okay, then du dx is 2 plus 9x squared. So du is 2 plus 9x squared dx. Okay, well, I've got 2 plus 9x squared sitting inside the integral there, okay? It's right there. So this looks like it's going to help out significantly. Then I'm going to change it over. 2 plus 9x squared over the square root of 1 plus 2x plus 3x cubed dx becomes, okay, this whole 2 plus 9x squared. Sorry, I've got congestion this morning. That whole numerator stuff gets replaced by du. And then I just have left 1 over the square root of u. And notice this problem a lot harder than that problem, okay? That's when you use, well, techniques of integration, and you're going to learn about a whole lot more of them next semester. But the idea is to make your problem harder. I mean, no, excuse me, make your problem easier, not harder. And it's a bit of an art. You have to learn to spot forms. And yeah, and when you first start with these things, you may not make the right choice at first. First thing you choose doesn't work, try something else, okay? And maybe use substitution is not what you want to use at all. It won't work for everything, but it does work for this problem. So we've reduced this integral, this one to this one. That's a lot easier than that. Now I can take the antiderivative, u to the plus 1/2 over 1/2 plus c. So that's 2u to the 1/2 plus c. And u was equal to everything under that square root. So it's 2 times the square root, or I can just leave it as exponent form, to the 1/2. Okay. That's a 2. Yeah, if I just had this problem, now let's see, that function is going to be continuous over certainly the positive numbers. And maybe more than that, because I have to figure out what, whether it goes through 0 at some point. So maybe you'd have problems with it becoming negative and the square root not being defined, but it's certainly continuous over the positive reals. So any interval in the positive reals would give you a continuous function, and that means there is an antiderivative. This has an antiderivative. But can I write it down? In terms of, oh, guess Mr. Levy's internet went out. Can I write it down in terms of our usual functions? That is, can I write it as, square roots or polynomials or square roots of polynomials or something like that? Probably not. Okay. I don't know of any technique I can use on this function. It was really important that instead of having this, I had the derivative of what's under that radical sitting inside that integral. As far as being able to write down what the antiderivative is in terms of our usual functions. Yeah, and you can't always find such things, even though the antiderivative exists. Okay, any questions? All right, okay, this is not going to be on the exam. It will be on your next week's homework. So let's see, Mr. Daniel asked me to do a problem off of the October 16th homework. So let's look at that. Okay, so I guess we will start reviewing right now. And that problem said, use the intermediate value theorem, which I'll abbreviate as IVT, to show that there is a root of the given equation in the specified interval. Okay, and there were two problems there. One was x to the fourth plus x minus 3 equals to 0. And the interval was 1 to 2. And then the second problem was cosine of x equal to x. And the interval was 0 to 1. Okay, so what does the intermediate value theorem say? It says that suppose f is a function continuous on the closed interval AB, and also that f of A is not the same as f of B. Well, then if capital C is a number that's between f of A and f of B, and I know, okay, f of A is not equal to f of B, but I don't know whether f of A is less than f of B or whether f of A is greater than f of B. So just say C is a number between them. Some number little c the interval AB such that f of little c is equal to capital C. Okay. And okay, are y'all still there?
Yes, ma'am.
Okay, good. Can't just look out and see you. Okay, not these days. All right, so we have an interval, AB, and okay, this time I'll make f of A bigger than f of B. So f of A is up there, f of B is down there. What this function says is that for any, okay, so there's some curve connecting those two points in the plane. Some curve, okay. What the theorem says is that if I pick any number between f of A and f of B, that curve has to cross that line that corresponds to C. So there must be some little c such that f of little c is capital C. The curve can't go from f of A to f of B without passing through that level capital C. Okay, so how do you use this? If you've got x to the fourth plus x minus 3, and let's see, and your interval, so interval was given. One, two. Okay, so actually, well, I gave you the open interval, but this function is continuous on the closed interval. And what the mean values theorem says, okay, you wanted to show that there is a root of the equation in the specified interval. So in other words, well, let's look at what happens here. Well, f of 1, my endpoints are 1 and 2. F of 1 is 1 plus 1 minus 3, which is minus 1. And f of 2 is 2 to the fourth, which is 16 plus 2 minus 3, which is 18 minus 3 is 15. Okay, so for this function, call that one, call that one, okay. Okay. Call that 1, and so that's 2. F of 1 was minus 1. I'm going to call that minus 1, and I'm going to squish this down, call that 15. F of 1 is minus 1, so that point's on the graph. F of 2 is 15. Well, to get from level minus 1 to level 15, the curve has to go through the x-axis. So capital C here is 0. And the intermediate value theorem, so 0 is between two, and this was minus 1, and this was 15. Okay, 0 is between minus 1 and 15. So the intermediate value theorem tells you that there is some number C in the interval from 1 to 2. And let me just write that as one's less than C less than 2. Okay, C, okay, I should have put, should have said such that. All right. There's some number C such that 1 is less than C is less than 2, and f of C is equal to 0. Now, that's all you need to do. Okay. So it did not say, the intermediate value theorem did not tell you anything about how to find this number, little c. It just says it exists. But that does show that there has to be some number between 1 and 2 such that c to the fourth plus c minus 3 is equal to 0. Okay, some number little c. Okay, so therefore, oops, math notation. There is some number little c in the interval from 1 to 2 such that what is it, c to the fourth plus c minus 3 is equal to 0. Okay. I do not know what it is, what this little c is, but I am guaranteed its existence by the intermediate value theorem. Okay, Daniel, does that help?
Yeah, I think it's really B that I had trouble with. I did all this the same way.
Okay, well, let me do the other one. The other one is not quite set up so directly. For the other one, okay, you have cosine of x equal to x, and you're given the interval 0, 1. Well, that's not in the form f of x is equal to 0. But I can get it in that form. If cosine of x is equal to x, that means cosine of x minus x is equal to 0. So the function we want to look at is cosine of x minus x. And again, okay, this function is continuous over all the reals. So in particular, it's continuous over the interval from 1 to 2, okay, and, or not 1, 0 to 1, okay, and let's see, f of 0 would be the cosine of 0 minus 0 would be 1, cosine of 1 minus 1. Okay, well, I don't know what the cosine of 1 is, but I do know that the cosine of 1 is less than 1, that 0 is less than the cosine of 1 is less than 1. Let's see, because the cosine, draw a picture. The cosine of x, okay, between 0 and pi over 2. Pi over 2 is about 1.57, so 1 is between 0 and pi over 2. And that means the cosine, okay, the cosine's 1 there, and it's 0 there, and it's coming down in between. So I know that 0 is less than the cosine of 1 is less than 1, which means the cosine of 1 minus 1 is less than 0, okay? And 1's greater than 0. So this was an aside. Okay. So we have the hypotheses of the intermediate value theorem are satisfied. And that means that since the cosine of 1 minus 1, which is f of 1, is less than 0, is less than f of 0, which is equal to 1. Okay, so 0 is between f of 1 and f of 0. And yeah, since this is true, there is some number little c in the interval 0 to 1 such that f of little c is 0. So that would say 8. What? So the cosine of little c minus c is 0. Okay. And draw a picture. F of 0 was 1. F of 1 was some negative number. Okay. Cosine of 1 minus 1. But the intermediate value theorem says that this function then f has to go through 0 to get from this point to that point. Has to go, it starts out at level 1, ends at level cosine 1 minus 1, which is negative. It has to go through level 0 to get from 1 down to cosine 1 minus 1. So that's true, and that means that the cosine of c is little c. Okay. And again, we don't know what this little c is. We know that it's between 0 and 1, but the intermediate value theorem tells you nothing about how to find it. And the intermediate value theorem, okay, sometimes you've got more than one choice. If you have a, say my function, let's see, I'm gonna make it do a whole lot of stuff. My function looks like that, all right? So f of b is over there, f of a is over there. That wasn't a good, okay, let me change it a little bit. Make it more exaggerated. Suppose it does this. Well then, now here's f of a right there. There's f of b. So I've got to pick a number between f of b and f of a. So call that c right there. But if that's c, then there's that point, and there's a point there. Okay. They're going to give me, okay, a needs to be moved over a little bit. So there's a point real close there. There's one there. There are 3 possibilities for c in this case. The intermediate value theorem just guarantees the existence of one, but it's not always true. There can be many. Okay. Does that help, Daniel?
Yeah, I guess if that's as far as we can go with it, yeah.
Yeah. Okay. Yeah. The problem does not ask you to find this number. Okay. It asks you to show that it exists.
Yeah, I made it as far as to getting to g of 1 or whatever,
Okay.
to cosine of 1 minus 1. So,
Right.
and then after that, I was just like, yeah, this is getting nowhere. So, yeah, that makes sense.
Well, no, you can't find it. Okay. Well, not easily. You can approximate it very well, know a few techniques, but yeah, so that's all you had to do in that problem. And oh, problem 5 was a little bit like that. Okay, what's time is it? Oh, 8:54. So it's time to quit. Okay, maybe we'll do problem 5 tomorrow.
So we don't have any problems like these on the exam, would we? The interval.
Yeah, you would. Okay. And I did post a practice exam. I suggest you work it tonight. So, and we'll maybe go over a lot of it tomorrow. Okay, but don't remember those exact problems are not going to be on your exam.
Right.
Yeah, there are representative problems. You want to make sure that you understand the whole family of problems that are like that. Okay, so I will see you all tomorrow, and hang around if you want to ask a question.
Good day.
You too.